I'd like to welcome you to today's webinar, Understanding the ACI 56221 Concrete Repair Code webinar series. This is part 3 of the series. We're very glad that you could join us today. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 2 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. Today's presentation is approved by the American Institute of Architects and the International Code Council, and this webinar has been approved for 2 learning units. The description for today's webinar is shown on your screen. It's also available in your handout. And today, Dave will be discussing repair methods, including surface repairs and structural strengthening, and explain some more on how to select the appropriate approach for a repair project. Our learning objectives for this webinar are also shown on your screen as well as in your handout. And now I'd like to take a moment to introduce David Tepke, our speaker for this afternoon. David Tepke, PE Fellow of ACI, is a Principal Engineer with SKA Consulting Engineers, Inc. He serves as the Building Solutions Manager in the Charleston office and specializes in structural and materials evaluation, troubleshooting, repair, and service life extension. He is a fellow of ACI and a NACE/AMPP certified corrosion specialist and protective coating specialist, and a participating member of a number of technical committees at ACI, including 201 durability, 222 corrosion, 301 specifications for concrete construction, and 329 performance criteria for ready-mix concrete, as well as ICRI Committee 510 on corrosion. And with that, I'd like to pass the screen over to Dave.
Thank you very much, Katie. I appreciate the introduction. All right, thank you very much. I'd first like to start by acknowledging ACI for putting together this webinar series and putting some really good examples together that we'll go through today. And also acknowledge Committee 562 on their work over the past 10 years. Or actually more than 10 years in developing the document that we'll talk about today. As a non-affiliated practitioner, I appreciate all of the hard work that they put into it to help us practitioners develop effective repair documents in accordance with industry standards. So with that, I wanted to first kind of summarize or go back a little bit in time to part 2. I know Mike Bartlett was talking about chapter 6 in terms of condition assessments. And as part of that, he talked at length, I believe, about the statistical nature of evaluating concrete specimens and steel specimens for evaluating material properties. And he went into that, again, at some depth. And so we'll start this presentation off with a few examples that illustrate some of the principles that Mike was talking about in Chapter 6 on assessment. And then we'll get into the Chapter 7 provisions, which is associated with the design criteria and information included in the code. So the first example that we'll discuss, and again, acknowledgement to ACI for providing the examples in the presentation. But the first example we'll discuss is in determining material properties for concrete specimens in accordance, structures in accordance with the code. So this particular example is for a historical building set in the 1930s. And what is being evaluated is the addition of a mechanical unit within the attic. The structural system being concrete framing, concrete slab with inverted T-beams. And so, as is frequently understood by those of us that evaluate existing structures, particularly for historical buildings, the material properties sometimes aren't reported or we don't have existing structural documents. And so this particular example shows that there's 2 number 5 top and bottom bars, 6-inch wide web, and an overall depth of 12 inches. And so the idea is, how do we estimate what the properties of the structure are? And so ACI 562 is applicable in this respect, and the licensed design professional then is charged with evaluating beam's capacity with the new mechanical unit, evaluating and determining the as-built dimensions, and determining cover depth to the bars. So to determine or evaluate the cover to the reinforcing steel, as well as confirming the reinforcing steel dimensions themselves, obviously some minor or some complementary, I would say, excavations are typically conducted to confirm and provide basis for calibrating the cover depth with a cover meter. So, like as mentioned, the existing documents in this particular example do not provide sufficient information to characterize the equivalent concrete strength or the yield strength that can be used for making calculations. So the code provides a couple of different methods in which one might then evaluate conditions and properties for making those calculations. Table 1 or table 6.3.1a is a table that shows permissible equivalent compressive strengths for structures of different eras. So for instance, we see footings, beams, slabs, columns, walls in eras from 1900 until today. And what you'll notice is that these are fairly low values, and by their nature, they are generally speaking somewhat conservative, but they would have to be in order to use default values. Similarly, with reinforcing steel, there are different steels that were, or different grades of steel that were available in throughout history. And so for this particular situation, and I should go back and mention that for the beams that we're evaluating from a 1930 structure, 2000 PSI would be the default value. Similarly, we'd be using 33,000 PSI yield strength for a structure built from 1911 to 1959 there. So we obtained the strength reduction factors from ACI 562, section 5.3.2. And in this particular case, when default values are being used, 0.9 is used for flexure and 0.75 is used for shear. So in calculation of the demand to capacity ratio for existing conditions, that is without the addition in the attic, is 0.9. So that's okay. The demand is less than the capacity. However, when the mechanical unit is used, the calculated demand to capacity ratio is 1.27. So this is representing a condition that requires strengthening because the demand to capacity ratio is greater than 1.0 when the additional mechanical unit is being installed. So based on this, the LDP recommends a material sampling program. And as Mike described in part 2 of the webinar series, it's permissible to take samples to evaluate statistically what the parameters are. So that's determining the equivalent concrete strength and the equivalent yield strength. The concrete core is based on equation 6.4.3.1, and I believe this was discussed in part 2. For 8 samples, N is the number of core samples tested. FC there is the average that was determined. V is the standard coefficient of variation. KC is the modification factor based on the number of samples, which gives an equivalent compressive strength of 5,095 PSI, which is greater than 2 times the value from the historical table provided. The steel reinforcement results using the equation shown for 4 samples, the average yield strength 42,225 PSI, but because of the low number of samples here and the modification factor on the variation, you can see the equivalent yield strength is about 33,000 PSI, which is pretty consistent with the historical numbers. what you'll notice there is that the coefficient of variation is pretty low, but the modification factor is high because of the number of the results. When you use sampling to evaluate properties, the code permits you to increase the resistance factors. So instead of 0.9 for flexure, when you're actually measuring the properties, you're permitted to use 1.0 for flexure and 0.8 for shear. So using these numbers, you get a revised demand to capacity ratio of 1.06 for beams with a mechanical unit. And again, the demand to capacity ratio is greater than 1. So this LDP, well, the two options were to strengthen the beams based on what was evaluated, or potentially collect additional samples for yield strength testing. And as mentioned, there were relatively few samples taken for yield strength testing, and so by taking additional samples, you can see the KS value, or the modification value, comes down, and because that variation is relatively low, you can see that there is an increase of equivalent yield strength there to 36,049 psi based on increasing from 4 to 6. And so what that shows is that when you get a better representation or a more confidence in the values that you are receiving, you potentially could be able to justify not having to strengthen. And so the other takeaway here is that when you actually do a sampling program, you can potentially get a lot better representation of what's in the structure, and show that it's adequate for the additional loads. So I know that this is something, this flow chart is something that has been shown before in part 2, and what we had been talking about, I think what Mike started to talk about and we were showing, is evaluating the in-place condition. Evaluation is the next step, and then development and evaluation of the rehabilitation strategies, and we'll talk a little bit about those. So the evaluation process, as part of the assessment, evaluation, and analysis of a structure, is to determine and to confirm the cause of deterioration. We know that there's a variety of conditions and situations that can precipitate deterioration in concrete. Of course, the one that a lot of people think about is reinforcing steel corrosion. There's also other deterioration processes: freezing and thawing distress, alkali silica reactivity, delayed ettringite formation, etc. So it's important to determine and confirm the cause of deterioration so that adequate repairs can be conducted. It's also then important to determine the extent of deterioration, and you can do that through a variety of techniques, non-destructive techniques, as well as visual techniques and destructive sampling. From there, you evaluate the appropriate and cost-effective remedial measures. There can be a variety of different ways to repair a condition, and logistics, costs, service life, and a variety of parameters come into play there. From there, also predicting the future deterioration of the repaired or unrepaired structure is important to understand and provide the owner with an understanding of their structure and what it may mean in the future. So if a member requires repair in accordance with the code, the LDP should determine if assessment is necessary on similar members within a structure and present recommendations to the owner. And again, when we're talking about reinforcing steel corrosion that might be precipitating in one member more than another because of maybe increased moisture, or perhaps alkali silica reactivity, delayed ettringite formation, something like this, other deterioration mechanisms, it might be where those conditions just aren't as advanced or outwardly observable in other structures. So it might be necessary to evaluate other members within a structure if something is determined. This could also be the case if you find low strength, for instance, in the member that you're evaluating, or if you've identified perhaps conditions that were deficient conditions during construction, such as reinforcing steel that isn't where it should be in accordance with the drawings, etc. Things that might give you indication that there are other conditions potentially that should be evaluated in other parts of the structure. So the goal of the structural assessment being to again evaluate those in-place conditions to help determine or evaluate the cause of the stress. The ultimate goal then is to refine and present rehabilitation strategies that are consistent economically and from a practical nature for the structure, and to be compatible with existing materials. Because unlike new construction, when we're repairing structures, there's a significant amount of thought that has to be given to how what we're doing, sometimes 30, 40, 60, 70 years later, potentially can impact load paths or impact performance of the existing structure, or in fact even influence the rate of deterioration in the future. So after the design basis code and criteria are determined, and I know Mike talked about that in part 2, there are a variety of conditions that are evaluated to determine what the design basis code is. Is it the current code? Was it the code during initial construction? And once that is determined, once the load factors and load combinations are determined, the material properties, as we just discussed and as part 2 discussed, and once we've evaluated the structure, at this point, it's necessary to perform the analysis. What does all of this information mean, and how does this impact both the existing structure and how the structure will perform in the repaired state? So the goal of the structural analysis of the existing structures is to accurately model the current condition of the structure as discussed, and with particular emphasis on the member under assessment. However, it's important to understand that the member under assessment can be impactful to other parts of the structure, and so it's necessary to look at the areas that could potentially be impacted by the member that is being evaluated or analyzed. So the structural analysis must consider the effect of sequence of load application, material removal, and it also must account for the material changes through the section. So as part of standard concrete repairs, obviously there's a condition where we're removing materials in order to correct some sort of an issue, oftentimes with conventional repairs, as mentioned. And so the removal of that material can potentially shift and redistribute load that can create overstresses in adjacent areas, or redistribution to impart deflections, etc. So as part of the analysis, the effect of that material removal, as well as the effect of the sequence of the load application and what it means when the area is removed in order to conduct the repairs, is of critical concern. Additionally, there are material changes through the section when a repair is conducted. You have situations where previous repairs might have different properties than the original construction, or the techniques and technologies that are being used to repair the structure can additionally create differences throughout the section that need to be accounted for. And so this is no different than really a design of a new structure. When you're analyzing a structure, for structural adequacy and for structural repair, you're really looking to satisfy equilibrium and compatibility. So in terms of, I guess, profoundness of these specific requirements, it really lays back onto sound engineering practice and judgment and analysis to satisfy equilibrium and compatibility, or the definition of deformations and strains, and to make sure that the analysis accounts for this. So the analysis, again, is going to account for and consider the as measured structural member dimensions. And I think, as part of the Chapter 6 discussion in Part 2 of this webinar series, it was discussed about measuring and evaluating the structural member and dimensions in order to confirm what is there and what is, particularly if no drawings are available, but even if original drawings are available, confirming those member dimensions becomes critical to ensure that there haven't been conditions that have changed, or there weren't original construction defects that can impact either the strength of the existing structure or the methodology or strength of the repaired structure once that's conducted. Evaluating the actual condition of the structure, including force redistribution that might occur from either the deterioration or the repairs. And we'll talk a little bit more during this presentation, for instance, external post-tensioning or original post-tensioning of the structure. And so the actual conditions of the structure, the deterioration, or what is actually in place can impact how forces are being distributed potentially to areas that weren't intended originally, however, are acting in that manner given the deterioration or previous or current repairs. So there's previous repairs and structural modifications need to be confirmed. Previous additions, for instance, do things look like they should have, like they were done with purpose? And are there any indicators that there weren't that things that weren't in accordance with the original design or confirmed are present? So previous repairs, structural modifications, these need to be addressed and evaluated. We sometimes see that previous repairs, particularly those that have not, followed industry standards, are failed or cracked or potentially not performing in the manner that the person that conducted the repairs had intended. And so sometimes it becomes necessary to evaluate those conditions to see if they're precipitating additional deterioration, or they need to be removed in accordance with the new repairs that are being conducted. Existing material properties of the structure, we talked about that already, and I think Mike covered that in Part 2 with regards to evaluating what the in-place conditions are, the effect of any alterations to the structural systems that were done intentionally, or maybe perhaps even those that have been less intentional. Actual loads that have been that are in accordance with the structure, and then interaction with the foundation and lateral drift. These are all things that should be evaluated as part of a performed analysis. In some situations, it might be difficult to confirm as-built constructions in current conditions. And so ACI 562 does permit the use of load testing to evaluate the existing conditions. And this is done in accordance with ACI 437.2, which is code requirements for load testing. Some conditions that might precipitate something like this is deterioration mechanisms. Sometimes it can be relatively difficult to ascertain specific properties of a structure that has undergone some sort of deterioration mechanism, because that condition can be highly variable along the member, and it can be to a different degree or extent throughout the cross-section of the member. And so evaluating or determining specifically how to evaluate the strength through analysis can be difficult in some respects. Alternatively, if there are conditions, construction defects, or conditions that can't easily be evaluated, then load testing can be used as a method to evaluate conditions. But it also can be used to confirm the effectiveness of proposed repairs. And so it's useful both in evaluating the existing structure and confirming that what has been done to repair the structure is effective. This is a load case study that was and the source is from structural, and so we'll show an example of how load testing was used in this case to evaluate the structure and selected repair approach. This particular example highlights the current office load, which was 50 pounds per square foot live load, but then was evaluating potentially new loads, 25 PSF superimposed overlay, and also 150 pounds per square foot live load. So extensive additional loads on the structure compared to the original. So the load test objectives, as indicated in this case study, were to determine the shear and flexural strength of the joists, and then perform cyclic load tests on both the unstrengthened joists and the joints strengthened with the overlay and carbon fiber reinforced polymers. So the field investigation shows that the dimensions of the structure, it was essentially a 3.5 inch thick flange, 6-inch wide web at the base, 26-inch spaced joist system from web to web. Steel reinforcement that was detected or determined in this field investigation showed that the steel reinforcement was 1-inch square bent bars. This is another highlight of reason for conducting at least a reasonable amount of excavations to confirm existing conditions to the degree that there's a level of confidence that you understand what the constraints and what the as-built and existing conditions are in their actual state. So the load test in the load test configuration that was selected, and essentially, obviously, we have a moment that is generated from a distributed load, and this load test approximated these loads by first detaching, and I'll show a picture of this in a minute, but isolating the member and then including point loads in at the third points to create a similar condition with respect to the loading. What was done in this particular load study or load test was to essentially include a reaction beam and a jack to install the loads and basically pull, essentially create a reaction beam to pull on the structure and then measure the deflection. And you can see the deflection measurements with LVDTs along the cross section. This is a picture of what it looks like, where you can see the pins in the jack with the W shapes, and you can see that there are point loads being generated with additional reaction points along those two W shapes. Saw cut was installed to isolate the section So the test configuration was for repaired portions of this load test study was to test joists in different with different conditions. You see the CFRP on the sides of the third test location, and for tests 1 and 2, the joists include U-wraps with CFRP. This is just a picture of the LVDTs and the setup from below. This is the measurement of deflection at the cut locations. And this is the tests where the bonded overlay was installed as part of the repair process. You can see there's the picture of the similar test setup with the bonded overlay. This is a picture of the bonded overlay, and what we can see are negative moment cracks, which should alert one to the fact that they are essentially indicating that there is good shear transfer across that bond line to a degree that helps provide that strain compatibility for transferring the flexural stresses to the tops of those overlays. Here are the load test results from this example, and there's a lot of numbers on the screen, so we're going to take it a little bit slow to kind of step through it. But you can see if we take the unstrengthened condition, which is the first row, you can see that the factored shear capacity of 8.8 kips corresponded to a live load of 92 PSF. And in flexure, the factored moment of 59 kip feet corresponded to a live load of 136 pounds per square foot. So the limiting factor in the unstrengthened condition was the 92 pounds per square feet as the maximum allowable live load. With the 3-inch reinforced concrete overlay and the carbon fiber reinforced polymers, you can see that the shear capacity was significantly increased to a degree that allowed, even with the sustained dead load, the additional sustained dead load of 153 pounds per square foot live load. And so the maximum allowable live load in this example, as provided, was 150 pounds per square foot through the installation of the CFRP and the 3-inch overlay. So confirming essentially with load testing that the calculated capacities were sufficient in accordance with this repair design. Wrapping up, well, talking a little bit more about Chapter 6, there are a number of references available for the guidance and specific aspects of performing the assessments for existing concrete structures, and this is just a subset of them, really. ACI has a lot of documents, ACI 201, durability and conducting condition assessment, ACI 228, which is on non-destructive testing and evaluating strength, 364, ACI 437 on strength evaluation. So there's a variety of different ACI documents. There are also other documents such as from ASCE and FEMA, and these are listed here, and these are obviously available in your presentation in the download that you can look at and reference as they provide some assistance in performing specific parts of assessments for existing structures. We're going to shift now to the design of structural repairs. So that was essentially wrapping up Chapter 6, which is on the assessment. We'll talk more in depth now on the design of structural repairs. And so again, this is a flow chart that has come up a few times in this webinar series, And at this point, we're going around down into the middle portion of it. So once the preliminary evaluation has been done, potentially dangerous structural conditions have been evaluated, and the design basis code has been looked at and confirmed, and the assessment's been conducted. At that point, Chapter 7 provisions of design for the structural repairs come into play. And so the remainder of this presentation is going to discuss the design of repairs, and then part 4 tomorrow is going to talk about the durability and construction aspects, et cetera, to round out the webinar series. So the learning objective for this module, as we switch gears from the assessment and rounding out what was started in part 2, is to consider the repair process. There are a variety of different repair techniques and technologies, from conventional to post-tension to FRP, et cetera, that should be evaluated and considered when looking to repair a structure. Obviously, maintaining continuous load paths, as is in good engineering principle, and distinguishing between different bond strengths for different applications. We'll spend a bit of time talking about bond strength in this next part of the presentation, and it really is one of the most important aspects, I think, of conducting repairs. When we're looking at conventional repairs, we're removing concrete and we're putting new concrete in its place, and that the efficacy of that repair is strongly impacted on how well stresses can be and strength compatibility is established between those areas, and how strong that bond is, and how to achieve that strong bond, and what bond strengths are important, and how to evaluate the need for testing or the use of interface reinforcement. And this is, again, as a practitioner unaffiliated with Committee 562, I believe this is one of the parts of the code that are very useful to the practitioner for conducting repairs in good accord with industry standards. So the primary purpose of repairs is to restore the structure's integrity, safety, and serviceability. Obviously, these all go hand in hand, safety being a very important aspect of what we do as engineers. And so maintaining the integrity of the structure, but also creating a serviceable structure that the owner can continue to use. Strengthening, as discussed in Chapter 7, is required to address existing strength deficiencies, changes in design loads, effective lateral loads. Perhaps, looking at the existing strength deficiencies, original construction defects, perhaps where the reinforcing steel wasn't where it should be, or the concrete strength isn't quite what it should have been, and such, to a degree that it impacts the capacity in accordance with what would be expected with tolerances that are standard in the industry. Existing strength deficiencies can also be a result of deterioration mechanisms. We'll talk a little bit about reinforcing steel corrosion in the coming slides, and I'll touch a little bit on some of the challenges that can occur with respect to that. Changes in design loads, either because conditions or needs of the structure are changing, or there's some other increase in desired use, and the effective lateral loads from the respect of potentially additional wind loads, et cetera, that might come to pass or be desired or needed for the function of the structure. The primary and principal function, and this was discussed in the previous parts, but again, this is no different than any other design approach that is a part of ACI 318 or other codes. And the primary condition that the design strength or the factored resistance has to be greater than what the loads on the structure, the factored loads. And so this is something that has to be satisfied within all sections during a repair process. The repaired structures, obviously, in repairing a structure, we're generally speaking, some things are being changed. Parameters or materials being used have to be able to provide adequate stiffness to limit lateral and vertical deflections, any vibrations that might be detrimental to the structure, cracking, as is a serviceability and potentially a durability issue, and then deformations that may affect the strength and serviceability, either from additional potentially ponding, if these are exterior components, or deformations that might create unbalanced or non-concentric loads on adjacent member. So again, and I've mentioned this several times already in the presentation, but this is nothing really new in accordance with any proper structural design, whether it be new or existing structures. You are looking to consider the loading, internal forces, deformations, and composite action. The difference here is that we need to evaluate it both in the existing and the repaired structure. A common example used in terms of understanding how during a repaired and an unrepaired state, or even during the repair process, conditions might impact and create potentially a condition that is undesirable, is in the repair of columns. Obviously, when you repair a column, particularly if it had some sort of corrosion or materials-related distress that has required undercutting or removal of concrete around the reinforcing steel bars, conditions can become critical with respect, in this case, to how much concrete is removed. What's the maximum amount of the column cross-section that can be removed? But also in the minimum unsupported bar length. Obviously, buckling loads and buckling capacity of the individual bars reduces substantially as the length of the unsupported bar increases. So considering these aspects when replacing sections of a column or other members really have to be evaluated. So considering the maximum amount of surface area or the minimum amount of or the unsupported bar lengths, etc., can be very impactful to the structure. And so limits for concrete removal and also the necessary monitoring requirements are specified in the repair documents. When shoring is required, and I know it's not on here, but when shoring is required, specifying the shoring loads, locations, etc., become important when the structure is being repaired to a degree that requires supplemental support. The ultimate goal when repairing these structures is that they're going to share load. And so to go back to the column analogy or the column example, just taking a step back, at the end of the repair, what's been installed has to work concurrently with the original construction. And so in some cases, good column repair requires deloading of the column, et cetera, to provide that ability for the new repair material to work in concert with the existing concrete. And the material properties that impact shrinkage and volume change become very important. But also in other repairs, anytime you're repairing concrete with these types of methods, you're relying on, again, I mentioned it before, but you're relying on the bond and the shear transfer and compatibility through those materials. And if the stiffnesses are vastly different between these sections that you are repairing or supplementing compared to the existing structure, load is going to be redistributed. And so making sure that those connections and stiffnesses are evaluated and considered such that you're able to, you're sharing the load as it's intended. I had mentioned before, well, I've mentioned several times in this presentation about the bond of the repair material and how important it is. And we're going to talk at length here. Next several slides, I think, is going to talk about the bond of the repair material and how it impacts the efficacy of the repair, and also how it impacts the need for potential testing and additional supplements. When we're repairing to improve just durability or aesthetics, we're essentially looking to make sure that there's composite behavior under service loads. But when we're looking for structural repair, we need to make sure that there's composite behavior, that bond is effective under both service and ultimate states, because it's that ultimate state, obviously, that dictates the capacity of the structure and provides for the safe use of the structure. But also in non-structural repairs posing life safety concerns. The example that comes up that I can think of off the top of my head is for corrosion-related repairs in overhead conditions, where or even repairs, any repairs really in overhead conditions or overhead areas, where if that repair material detaches, it can essentially fall and cause injury to people or property. And so balcony soffits, where there's deterioration and distress on a soffit, whether it's structural or not, whether there's reinforcing steel in it or not, can pose potential life safety concerns. And so composite behavior is important in those conditions to ensure that safety for the public is maintained. The critical part of evaluating bond for repair material and in a general repair is to evaluate the stress transfer at the interface between the repair material and the existing structure. Obviously, we know that shear is a primary impact or a primary actor on many repairs, especially those, obviously including those, I would say, that are in flexural members. Then also tension can be another important aspect of the bond of a repair material, and sometimes shear and tension need to be considered both. But it is very critical, and a lot of time is spent in committee work, a lot of time is spent in different organizations talking about surface preparation as it affects and impacts the bond of the repair material. When we look at repair materials, a lot of people are worried about what the compressive strength is, but the bond of the repair material to the substrate is of critical concern, and oftentimes much more important than given the fact that the repair material is of quality and has a compressive strength commensurate with what is needed for the repair. Bond strength, and as influenced by surface preparation, is a critical parameter. And so that bond strength is going to be influenced by the quality of the surface preparation. We'll show an example here coming up about surface preparation and how it can impact bond strength. The strength of the concrete substrate itself, when there's deterioration or distress in the concrete, or if it's very low strength concrete, the substrate conditions can be an important factor. The characteristics of the repair materials, repair materials have a variety of different, especially bag materials, have a variety of different characteristics, some of which can be more beneficial to establishing and maintaining long-term bond. We often cite volumetric change because not just load parameters can impact the the shear stress on a bond line, but also shrinkage and temperature effects of the surface can impact stress on the bond line. The strength of the repair material, as mentioned, comes into play, but again, often is not the most critical parameter with respect to a structural repair, given that it has adequate strength for meeting the structural and durability needs. And then construction procedures can impact, and the most notable one is how to condition the surface. Whether it's saturated surface dry, whether there's a bonding agent, these sorts of things significantly can impact the bond capacity. So interfacial shear, and for instance, if we just look at a beam in bending, as that beam bends, we know that there is shear transfer across the section, and that shear transfer is then therefore has to transfer across the repair section that is shown here in the bottom part of the diagram. But there's shear that is transferred across there, and if you recall, just typical shear stress equations that dictate or indicate the shear stresses that develop across different sections as they are maximum at the center of the section and taper towards the end of the section. So those shear stresses develop both from loading and, as mentioned, from time-dependent deformations that may occur from shrinkage. For instance, in a new corbel that's installed, obviously we have shear that is required across that interface, and in accordance with ACI 318, there's, and what we'll talk about in a few minutes here is how that reinforcement across that interface impacts that continuity, and also what's required in terms of capacity for shear. So in accordance with section 7.3.2, the repair design needs to account for the force transfer at the interface between the member and the repair material. And so, again, to satisfy strength requirements, the shear stress, the nominal capacity shear stress has to be greater than the applied stresses from shear across the interface of the repair area. For ultimate shear, or for shear less than 500 BVD, which basically is 500 PSI shear stress, interface shear is designed in accordance with ACI 318, section 16.4.4. And again, you can refer to ACI 318 for these equations, but essentially for new concrete placed against concrete, existing concrete intentionally roughened and including steel dowels, there's an equation for capacity there. And again, this is for conditions where it's less than 500 PSI shear stress. There's a requirement for minimum interface reinforcement, which is provided by these equations based on the compressive strength of the concrete or the yield strength of the steel, the spacing, the width of the members. And for new concrete placed against concrete not intentionally roughened, to include a minimum amount of dowels, the permissible shear stress is 80 PSI, and given basically by the ultimate, or the shear capacity, the nominal shear is equal to 80 times the width times the depth. So for new concrete placed against concrete intentionally roughened, similarly, it's 80 BVD. In a case where the shear stress is greater than 500 PSI, or the ultimate shear is greater than 500 BVD, then the shear must be completely resisted by interfacial steel reinforcement. And essentially, it takes it into a section of the code where it's considering shear friction based on the friction offered by the interfacial zone. And so ACI 562 has basically some analogous features and essentially refers to ACI 318 in this respect, and provides testing requirements where the shear stress is partially or totally resisted by the concrete. So in conditions where the shear stress is less than 30 psi, the section 7.4.2 requires bond integrity testing, and we'll show you what that means in a minute. Where it's between 30 and 60 psi, quantitative bond strength testing is required, and where it's greater than 60 psi, quantitative bond testing is also required, but interfacial shear, interfacial additional shear items are necessary as well. So we'll talk about this. Essentially, dowels. Non-destructive methods when it's less than 30 psi are, for instance, hammer sounding in accordance with ASTM D4580, impact echo to evaluate the bond line in accordance with ACI 228 and ICRI 210.3, and impulse response is another example of a technique that can be used. So again, when it's less than 30 psi, there's lower bond stress. What the code is really requiring is that evaluation is necessary to confirm, from a qualitative perspective, what the bond integrity is. When it's above 30 psi and less than 60 psi, the code is requiring more quantitative, and the primary one that is referenced and that people are using in the field is pull-off testing. And while it's recognized that pull-off testing is not evaluating shear performance, it is providing some information with regards to the integrity of the bond line. And so there are some parameters included in ACI 562 for conducting testing, particularly pull-off testing, and minimum amount of sampling. And then also it's the requirement of the licensed design professional to evaluate those and specify the necessary level of or values for applicable bond testing. But there's some information in 562 to help that along. And there's other documents, ICRI, I believe 210.3 is another one that provides some guidelines with regards to specifying bond stress, pull-off stress as well. There's also splitting tests, slant shear tests that are not often used. Again, the pull-off test can be done in situ, and even though there's some variability with it and some recognized conditions associated with running the test, and it's still often used in the field to evaluate. So if VU is greater than 60, it still requires bond testing in accordance with what we previously talked about, where it's between 30 and 60 psi, unless VU is completely resisted by interfacial reinforcement, and then testing is not required. And so in that case, and again, that 60 psi is basically 0.75 times the 80 psi that was referenced when we talked a few slides ago about from ACI 318. And so that's where that 60 psi derives from in helping evaluate whether the need for interfacial reinforcement. So again, that's a very important part. I think a very helpful part of this code with respect to practitioners is helping people understand that the bond is an important aspect. The testing and use of interfacial reinforcement where necessary can be very important for providing that continuity between repair areas and the existing structure. Again, I touched on this a little bit, but repair material selection is very important, and the physical properties are important with respect to the durability, the thermal movement of the repair material, the volume stability with shrinkage, etc., but also the adhesion or how well it adheres to the existing structure is very important. Environmental conditions come into play. Some materials are very, they set more quickly, and some have extended set. And so selecting the repair material to be effective for the particular condition is of importance. Other parameters, obviously durability, corrosion resistance. Sometimes if you're using cathodic protection or other service life extension measures, the electrical properties or the resistivity of the repair material comes into play and becomes very important as well. So some other guidelines that are provided for the selection of repair materials. There's a variety of them, ACI 318, ACI 301, 503, 440, and also a variety of ICRI documents, as you can see here. And again, these are all listed here in the presentation that you can reference in the future. With having talked about the bond strength and the necessity of potential interfacial reinforcement and also the importance of bond, we're going to now switch gears and talk about some of the methods to strengthen the structure. Conventional reinforcing or conventional repair methodologies that primarily include removal of concrete or some use of concrete to create some additional capacity, post-tensioning, and FRP. And so ACI 562 includes provisions in Chapter 7 for post-tensioning and FRP, which provides some guidance requirements for the licensed design professional. So conventional strengthening methods, and I think this is the one that many times are used, either repair of the structure, again through removing material and replacing it, which might include supplementing the reinforcing steel if there's deterioration and distress, potentially creating some concrete enlargement, or in some cases adding supplemental structural steel. When we're talking about concrete enlargement, maintaining fire rating requirements with cover over the reinforcing steel, and we'll talk a little bit more about the requirements in the code with regards to fire. But also the other important parameters here are, again, that composite action that's established through the bond that we talked about. Clearances can oftentimes be a parameter that needs to be evaluated, making sure that the minimum heights to maintain clearances with respect to the code or functionality of the structure with respect to the owner's needs. As with all repairs or repair methodologies, cost and access become critical, as well as load sharing. And again, we talked a little bit about that with regards to columns, but making sure that the loads are getting into the repair areas or into the strengthened areas to accurately or to adequately share them as is evaluated and required by the analysis. So ACI 364.10T, which is a tech note, provides some information with respect to what to do when bars are corroded, in evaluating the cross section and helping to determine what the effective development length is. If the bars have lost their ribs, then effectively they need to be treated as smooth bars. The tech note goes into and talks a little bit about how much corrosion is usually okay. And so an often quoted amount of, if you have less than 90% of the bar remaining, there can be concerns or at least need to evaluate it. But really, the licensed design professional should evaluate corroded reinforcing. As can be expected, there's oftentimes some subjectivity, frankly, that comes into play when you're evaluating corroded structures, and the experience and knowledge of the licensed design professional needs to come into play when evaluating a corroded structure, helping to understand what happens if there's spalling, how does that impact compatibility, and how does it impact the composite nature, et cetera. And so with respect to repairing these sections, there's requirements in the code for evaluating and repairing, and it's of critical importance when there is deterioration. Steel strengthening, obviously requirements for evaluating the fire rating. Is it exposed steel? Does it need to be fireproof to be consistent with the original structural system? As with the other methods, clearances and costs and access come into play, but then also stiffness considerations. Sometimes you might need to increase the size of the steel member to create an equivalent stiffness to a concrete member that is, either replaced or was needed. And so considering the stiffness and flexibility of the members that are being installed, because they can actually that can impact the structure or the portions thereof that are left in place and that are being supported by the new members. Post tensioning as a strengthening method is another condition that's evaluated or is included by the code. Obviously, the consideration for bonded and unbonded pre-stressing, and this in terms of looking at original, the existing conditions, whether it's a pre-stressed member that's potentially a precast member that has bonded tendons, or if it's unbonded pre-stressing from unbonded post-tension structures that are cast in place, can be very important to evaluate that and understand how the deterioration mechanisms might impact repair of those structures. Obviously, unbonded pre-stressing, if there's localized deterioration, it can impact additional portions of the structure, and so evaluating those how that load sharing occurs with adjacent members or even into multiple spans with regards to necessary shoring, et cetera, comes into play. With regards to repair included in post-tensioning, external post-tensioning, obviously fire rating of any external post-tensioning, as well as evaluating how that additional post-tension could put additional stresses on a member, such that design and analysis should be conducted to evaluate those conditions to make sure that the external post-tensioning is working as intended. So an effective method for repairing for sure, but as in all considerations, just ensuring that the loads that are being imparted by the additional post-tensioning is compatible with the structure. FRP is also addressed in ACI 562 code. Fabric bars and plates are all methods that can be used to repair a structure in design consideration, and there's an example that we're going to be going through here in just a few minutes. But the types, the fire rating, obviously clearances, costs, and access, and load sharing are all important aspects, just as in any repair method. So FRP, generally speaking, should only be installed on sound concrete. Applications are generally categorized as bond critical or contact critical. Bond critical are those applications where it's critical that the FRP is bonded to the concrete, and the action is created through that bond, through that stress transfer, that bond, strain compatibility through the bond. For instance, if you're strengthening with respect to shear or flexure, contact critical is where the FRP, the contact, the connection on the contact between the FRP and itself is of critical importance. And you can see in the lower left picture there is, for instance, where you are confining a column, contact critical situation. ACI has a number of documents that are applicable for the design, including those that address externally bonded FRP, internal reinforcement of FRP, and internal post-tensioning or pre-stressing with FRP. So the design of structural repairs in detailing considerations is going to include the effects of the modifications to the existing structures, the geometry, damage conditions, any loss of pre-stressing force, and also the repair sequence that can become very important when you're removing or repairing large sections, particularly when you're repairing large sections of the structure, but it certainly should be considered as part of all repair methodologies. This is an example that's provided, that ACI has provided with regards to floor slab strengthening. And we're going to work through this example, which is going to demonstrate the evaluation of the structure and potential strengthening method. So this is a plan view of a portion of the structure, which is a 6-inch slab, in which being evaluated for external bonded FRP reinforcement. The design loads are a sustained dead load of 10 PSF and a live load of 40 PSF, and the live loads vary to some degree around the structure. The top steel bars in general are number 4s and number 5 square bars at 12 inches on center. The bottom steel bars are number 4 square bars at 12 inches on center. And the steel bar depth is 1.5 inch from the bottom and 2 inches from the top. And so these are generalities with respect to the slab, even though it differs with respect to what was identified and also really what was required in the slab. So as part of the investigation in this example, ground penetrating radar was used to identify steel reinforcement. Again, whenever you're using non-destructive technologies, which are very useful and a good method to evaluate a structure, but confirming conditions and calibrating the results for the specific conditions becomes of importance. Semi-destructive testing was conducted on this particular instance for coring and drillings for the slab depth and to confirm conditions. So this is just the loading scenarios with respect to the slab, the portions of the slab. The self weight's a 6-inch slab. The superimposed dead load is 10 PSF, and again the live load is 40 PSF. So the dead load moment was 53 kip feet, and the live load was 27 kip feet for the area G to H 5 to 6. So again, there's a good bit of information on here, but essentially what you can see is there's different slab strips for the slab system, and you can see the slab strip widths there. The slab thickness is pretty consistent, and then the drop panels are shown in the column strips there. But what we see in what's being highlighted with the red numbers are where the applied loads are in excess of the factored resisted loads. And so you can see that in these strips, you can see that MU is greater than FMN, indicating that there is a concern. So the idea represented by this this example is to use FRP design in accordance with 440.2, where essentially the upgraded moment capacity is going to be the existing moment capacity plus that provided by FRP. And so what's shown here is the nominal design values and properties in tabular form for the FRP sheets. And in accordance with the design from 440.2, you can see that there's a reduction factor for environmental exposure, in which 0.95 was used for these interior exposures, applied to both the ultimate tensile strength and the rupture strain. This is a particular section, again, column G at line 5 to 6, east-west top surface with the FRP. And what you can see is the use of a 1-ply 12-inch wide V-wrap at 30 inches on center. The minimum strength requirements for ACI 440.2 for strengthening is that the original or unstrengthened section has sufficient capacity under 1.1 dead load moment plus 0.75 live load moment. And that's because of certain damage requirements that can occur, damage situations, fire, etc. It's necessary that fire be accounted for, and that structure unstrengthened has to have an amount of nominal capacity essentially under service loads. So in this case, FMN, the original 68 kip feet, is greater than 1.1 moment dead plus 0.75 moment live, which is the 58 kip feet. So that's okay. That means that the structure in and of itself can resist those loads, notwithstanding the strengthening. So in the top surface at column G56, we see the slab is deficient at the interior supports, where FMN existing was 68 kip feet, was less, which is less than the applied moment of 75 kip feet. So adding that strengthening 12-inch wide at 30 inches on center increased the capacity to 135 kip feet, which is greater than that 75 kip feet applied, which is adequate for the strengthening. So on the bottom, for instance, from 5 to 6 and G to H, we see that, again, need to check that the original moment capacity of 32 kip feet is greater than the applied at 1.1 times the dead load moment plus 0.75 times the live load moment of 31 kip feet. So that's of importance to confirm again that the capacity unstrengthened is adequate to meet that load criteria. Again, including the strengthening, one layer, 12-inch wide at 60 inches on center, the upgraded capacity of 57 kip feet is greater than the 44 kip feet ultimate moment, which again demonstrates strengthening. And so this is just a picture showing the top surface and bottom surface plan for strengthening with respect to satisfy the requirements of the repair approach. Chapter 7 also has requirements for fire and elevated temperature consideration. The most notable which is the requirement to comply. If there is sufficient capacity in the existing structure, then no additional or supplemental fire protection is necessary. And that's discussed in 7.9.2. The reduced member properties is accounted for in section 7.9.3. And in addition to the performance of adhesives, any potential supplemental fire protection and the requirement of the fire rating of the repaired systems in compliance with ACI 216.1. And so Section 7.9 details the requirements of the code with regards to compliance in this respect. There's also the concept of virtual strengthening that's discussed here. An alternative to strengthening of an existing structure, if there's some sort of a deficiency, is to virtually strengthen it with regards to either reducing the loads on the structure, confirming that the existing material properties are higher than those intended for the original design. And we showed that, or we talked about that in the very first example that we discussed at the beginning of this, where the compressive strength or the strength of the structure was considerably higher than was originally, I guess, analyzed for. And then actual capacity by full scale load testing, such that we discussed with the second example that we discussed today. So, if the structure has issues, there are confirmatory methods to evaluate. The last example that we'll talk about today is a bond example. Again, we talked about bond being of critical importance and is a very prominent feature in Chapter 7 of ACI 562. So the bond example that we'll go through here discusses a project, and again, this was an example provided by ACI that the bond example here, which highlights the importance of surface preparation with respect to compliance. So this is a building that was constructed in 1971, a 9-story parking structure located in the Midwest United States that included an 8-inch thick lightweight concrete flat slab. F prime C was 3750 and 60 KSI yield strength ASTM A615 steel was used. And this is from the existing plans and specifications. And again, it's an appropriate approach in accordance with ACI 562 to use information based on existing plans and specifications if desired by the licensed design professional. So the preliminary evaluation, visual inspection, evaluated and reviewed, in this case, that the top surfaces of the decks were badly deteriorated. It was reported here 30 to 70% deterioration. And the bottom surfaces were delaminated and cracking as well. And you can tell that there is evidence of reinforcing steel corrosion, and there's low cover as shown in the picture on the left, and fairly large areas, and low cover in the soffit areas on the right. So primary concern when you see this in the preliminary assessment is that there are potentially dangerous structural conditions or potentially dangerous conditions, not necessarily or at least not confirmed yet through structural analysis, but overhead detachments can present a structural or a potentially dangerous condition that could be a hazard to the public. And so again, the source here is Tadger Cohen Edelson Associates for this case study. We see the evaluation is in the evaluation, cores were extracted from several areas and tested for compressive strength and chloride content. Chloride content being of importance when you are evaluating the corrosion potential of reinforcing steel in concrete. There are a variety of other techniques that can be used as well if deemed necessary by the LDP with respect to evaluating deterioration and corrosion characteristics. So the test results in this case study, as reported, that the actual equivalent compressive strength matched that in the design. So there, in accordance with that, it wasn't really essentially any benefit found with respect to what is in place compared to what was designed. Chlorides, as is reported here, were present over the full depth, and there was insufficient cover at various locations. And the source is concrete diagnostics here. So the repair design consisted of removal of 3.5 inches of top deck of the slab and replaced with a bonded lightweight concrete overlay. So for any overlay, and overlays can be one of the most challenging operations because you're dealing with, generally speaking, a large area that has to be adequately prepared and oftentimes time-sensitive operations. For instance, moisture conditioning the surface, creating a good bond, however that's being accomplished, whether it be with a bonding agent or with a scrub coat of the repair material. But conditions can be highly time sensitive with that respect. And also the large area that has to be confirmed to have good surface preparation. So it can be somewhat challenging to do a bonded overlay unless very good quality control and good specifications are included. Removal of deteriorated concrete is of importance, obviously, because attaching new overlay material to existing structure is going to be dependent upon the capacity of the area to remain. So removal of all deteriorated concrete is of importance. Cleanliness of the surface to remove latents and bruised or damaged concrete, and then ensuring that the surface is properly roughened to that required by specifications. The profile can impact again, going back to that shear capacity of the bond, profile of the surface, as well as how clean it is and how sound it is, all impacts that shear capacity. So removal of all loose material and detrimental materials that interfere with bonding or curing of the overlay is of critical importance. There are a variety of different methods that are used for removal, starting off with cutting. Cutting around the repair area is important. It's critically important that the reinforcing steel is not cut when the concrete is being cut. So oftentimes our requirement is to ensure that you're at least a 1/4 inch away from the height of from the cover of the steel, so that you do not cut through any reinforcing steel that is a necessity for the structure. Repair geometry is of importance, and when you're dealing with reinforcing steel corrosion that results in spalls, what's often occurs is that there'll be spalls that generate in small areas, and when you try to repair just the areas in odd geometries that have many reentrant corners, stress concentrations develop, and as that repair material shrinks or volumetric changes occur from environmental conditions, cracking can occur. So it's ideal and beneficial to create simple geometries. It's also often necessary to extend the repair areas to include corroded reinforcing steel or areas that have not yet manifested as surface issues that have conditions of corrosion or bond deterioration between the concrete and the steel at areas that perhaps aren't cracked in a macro sense or haven't spalled yet, or haven't significantly delaminated yet. So depending upon the repair approach and the surface life extension, whether some sort of corrosion arresting methodology is used, it can be necessary to remove more concrete as well in that respect. So this is just showing that the areas the areas of removal are greater than the areas, generally speaking, of spall deterioration. And generally speaking, again, you are removing the concrete to where corrosion is occurring and inhibiting the bond capacity, and again, in accordance with whatever service life extension approach is being used. Undercutting the reinforcing steel bars or removal of the concrete around all reinforcing steel is often necessary. And this is again just showing that removal of concrete in isolated places is not a good approach because of the stress concentrations that develop. So that repair area on the left would include removal in a simple geometry. The other thing that's a concern or critical is that large variations in depth aren't experienced, because again, creating steel concentrations, and again, not to cut existing reinforcing steel bars. Chipping is an approach, mechanical removal approach, that's often used to remove repair materials. And again, the idea is to remove deteriorated concrete. This is just a picture of the surface showing concrete that has been removed. The other critical aspect is when you use chipping hammers, etc., bruised or micro-cracked concrete occurs, which then has to be removed in order to create that a good bond surface. ICRI has molded standards to help visually observe and identify the level of surface profile, and these are called CSP, concrete surface profile chips, labeled 1 through 10, and they get progressively higher amplitude as you go from 1 to 10. And so visually, these chips are used on a construction site to compare what has been done compared to what the requirements in the specifications might be, or what the requirements of the repair material manufacturer might be. The other approach that is often used in conjunction with chipping is removal in accordance with either shot blasting or sandblasting. And shot blasting and sandblasting both act to, although they don't create as large of a surface profile as chipping, what they do is help remove bruised and microfractured concrete that can be a result of chipping. This helps remove all that the distressed concrete at the very near surface area for creating, again, a sound bonding surface. Hydro demolition, which is shown here, can be used as an approach to remove unsound and deteriorated concrete as well as sound concrete, and it creates, generally speaking, can create a profile with significant amplitudes, and it also has a low propensity for bruising and microfractures. And so you can see here is a picture of a hydro demolished surface that has hydro demolition. You can see that it has a very good amplitude. So again, when that repair material is placed in intimate contact and scrubbed in or otherwise confirmed bonded to this surface, it creates a good surface for again resisting those shear stresses that can develop. So this is an example of a 1/4 inch amplitude, and in fact, with hydro demo, depending on the concrete, you can get even greater amounts of amplitude than is shown here. So in this particular example, the contractor and the licensed design professional decided hydro demolition because again, it resulted in a rough, irregular surface. It minimized the surface micro cracking that we talked about that can occur from chipping hammers. It exposed aggregates and didn't fracture them. And it helps to selectively remove lower strength and deteriorated concrete. It minimized vibration to the surrounding structure, and it also preserves and clean the reinforcing steel bars for the project. This particular case, robotic equipment that was used for the hydro demolition, and a mock-up was installed and extensively tested. In accordance with that tensile bond test, as we discussed earlier, in accordance, again, ACI 562 has provisions for use of bond testing in accordance with ASTM C1583 when evaluating concrete repairs. And so, for instance, in this particular example, mock-up was installed and tested using extracted cores and a pull-off method. So this is some results, and the critical part of this results. I don't think it's important for us to look over on the left at the test locations or the test numbers or even the bond forces. What we're really looking for there is the bond strengths and the separation planes. When you're conducting tensile bond strength testing, certainly it's not ideal to have failures in the repair material itself, and it's not ideal to get bond line failures. Really, it's ideal to get substrate failures that are deep within the substrate, or those that have very high bond strengths that show that there's significant capacity. And ACI 562, based on different guide documents, provides guidance to the designer with respect to specifying bond strengths for tensile bond pull-off. There's documents that indicate potentially use of 100 psi tensile bond pull-off strength for non-critical applications, or and potentially higher than that for bond critical applications. But that needs to be used in conjunction with on-site conditions as well. So you can see here that during this mock-up, bond strengths were over 100 psi and ranging up to 157 psi. This is just a picture of project, and so during the project, the LDP required testing and noticed variability with regards to the bond strength. Some bond strengths were significantly lower, some failing in the substrate, which potentially gives concern maybe to if there's still deteriorated concrete in the substrate. Some that failed at the interface between the substrate and the overlay, which potentially can be a result of surface cleanliness operations, etc. And so it was observed here that bond strengths were lower than was observed in the mock-up. And so generally speaking, this gives interest in investigation of the issue. There are ICRI, the ICRI document referenced in ACI 562 provides some information with respect to interpreting and also specifying acceptable values in construction compared to what's observed during the mock-up. So the LDP in this respect, because he was getting variable, or he or she were getting some variable results, ordered the testing of samples. The results revealed that the contractor did not remove all of the loose material and debris, and so this is observance of some of the debris left after scarifying the surface. I've also, in projects that I've been involved with, have observed situations where excessive moisture has been left on the surface that has created a weak layer in the overlay material directly adjacent to the at the bond line, which has created low strengths. And so there's a variety of conditions directly adjacent in the substrate and at the bond line that can create problematic conditions. So the corrective actions were implemented to improve the bond strength, improve methods to clean the surface, remove residue resulting from hydrodemolitions, and more closely examine the substrate of the surface. And so the test results observed were more consistent and higher after these conditions. So the LDP ordered another set of petrographic testing on some of the samples to show the intimate contact between the new overlay and the existing concrete slab. So I guess the important takeaway here is that while pull-off testing can be somewhat variable, it can be useful and helpful in identifying issues with regards to bond and bond capacity and tensile bond strength. And also petrography can be helpful as well if conditions are identified through testing that call into question the bond capacity. So with that, again, the next part 4 tomorrow is going to talk more about durability and the remaining portions of the code. But I would entertain any questions, and I do thank you for your attention and the webinar today.
Okay, thanks, Dave. Our first question is, if you test the concrete strength by taking concrete cores and you have the original design drawings, but you do not sample the reinforcement, are you allowed to use the reduced fee in table 5.3.2?
A good question. I'm not aware of that being permitted. I'd have to dig back into it, but my interpretation of that would be that if you are using in any capacity the existing the documented values, then you would use those limiting fee factors based on that condition. What I can do is go back into the code and look a little bit more specifically and provide a response to that.
Okay, great. Our next question, did the load testing of the repaired joists include long duration loading?
In fact, we talked about this a little bit earlier on today before the webinar, and the cyclic, is my understanding, the cyclic load testing was conducted because of the amount of time and the reduction in time that could be done. There is some information in ACI 562 in the commentary that discusses the selection of cyclic versus monotone or mono testing. So there again, referring to the commentary there should provide some guidance, as well as looking in ACI 437 with regards to the use of the data that comes from that.
Our next question, does the code require special inspections of deliberately roughened surfaces to assure that the roughness isn't impaired by field procedures, particularly grouting?
The requirements in the code are for the LDP to specify testing and require testing based on the interfacial bond capacity, and so that's what's required in the code with respect to that. There are items in the commentary that discuss the qualifications of an inspector that evaluates it. And I know one such qualification is the ICRI concrete surface repair technician, which as part of it includes the parameter or the requirements and procedures for evaluating the bond strength.
Okay, one of our attendees is curious if you could discuss the meaning of bruised concrete. You did mention that when you were talking about surface preparations.
Yeah, bruising in the concrete is a term that's used in the industry to discuss inconsistencies or slight deterioration or distress directly adjacent to the concrete surface that results from the impact of chipping hammers, etc. So in the area that's directly below and at the bond line, you can get what's termed bruised concrete, which is essentially distressed concrete that is even very difficult to see by the eye in that very near surface area.
Okay, we've got a couple questions related to bond and bond testing. So the first part is, does ACI 562 or other documents that you're aware of give a relationship between the various types of bond strengths? In other words, is there a way to relate direct tension pull-off strength or slant shear, etc., to shear bond strength?
So I am aware of some research that's been done in that respect, and it's a fair question, because what we're doing when we use tensile bond testing is testing the tensile capacity of the bond line, but in general, the shear stresses are what are of importance. And so I have seen there is a document that was recently published. I think Scott Tarr was one of the authors, who discussed the relationship between the shear bond capacity and the tensile bond capacity, but it is somewhat of my understanding, based on what I've seen in the research, it's somewhat of a loose relationship, because that shear bond capacity is highly dependent upon the amplitude as well as the adhesion.
Okay, and the second part of this question related to bond and bond testing is, are you aware of research regarding the flexural strength of a slab or beam element with the bottom cover blown off from corrosion, but with very little loss of steel area, and the concrete directly above the bars is in good condition and is bearing tight onto the bars? Addition to this question is, I would add that the bottom bars beyond the delaminated soffit concrete are bonded into sound concrete. Since the bottom cover is not part of the structural depth of the section at positive moment area, has the bending strength been much reduced such that expensive soffit patching is required?
I have seen some research a while ago with regards to the capacity of corrosion damaged concrete. What I will say with regards to soffit concrete is that, and I think what the question is saying is, if you had a long section of reinforcing steel bar that is anchored into the concrete and no continuity in the middle, there's a couple of potential concerns there. Number one is the development length of what is left in the concrete adjacent to it to develop those tensile capacities. The second would be the shear continuity, or the continuity in the primary section between to establish or to satisfy flexural beam theory. And then the third would be the corrosion protection of the existing reinforcing steel bar to prevent more substantial deterioration.
Our next question is, where testing shows the presence of high chloride content, what are possible repair measures to mitigate further deterioration of reinforcing after the repair?
So ACI committee document 222R, which was last updated in 2019, provides some information on this. There are a variety of things that can be done. The first of which is to remove all contaminated concrete such that it isn't in play anymore. That often can be cost prohibitive. I'm not saying it always is, but there are electrochemical methods, cathodic protection, which is can include galvanic protection or impressed current cathodic protection that can protect steel in the adjacent areas. There are additionally other electrochemical techniques, chloride extraction, that can be used. And so there are a variety of service life extension actions that can be done to help protect the steel and the structure. Oftentimes what happens when you patch an area that has corroded, you create a highly corrosive condition, or you've repaired that area, you've essentially turned what we call a notic into a cathodic area, and you create corrosion adjacent to it. I think Kyle will be talking more in depth tomorrow when he talks about durability and how that is associated with repairs as well. But there are techniques and technologies to extend the service life of the structure at whole when repairing just damaged areas of the concrete.
All right, our next question is, regarding the repairs for shears, are added dowels required to be developed on both sides of the shear plane? This is often difficult to do with many existing conditions.
ACI 318 has requirements essentially for the shear. Sometimes what we've looked to do is use hairpins or through bolting to create positive anchorage for development adjacent to. There's also headed reinforcing steel bars and the like that we've used in the past to develop reinforcement in a short distance.
And the final question we'll wrap up with for this afternoon: when do you need to submit repair for permitting, or when do you need to submit for permitting for repairs?
Depending on the jurisdiction, I think I'm not entirely sure what the question means, but typically they get submitted when the contractor goes into construction. But in general, conditions that impact the code, impact requirements of the code require permitting. And I think jurisdictionally, that can be interpreted in a lot of different ways. What I tend to always do is reach out to the code officials early on in a process and get them engaged. I feel that that's a way to help the project along, because then it becomes very clear what they do and don't want to see, or what they may need to see during the process.
Okay, great. Thank you, Dave, again so much for spending your time and sharing your expertise with our attendees. Just want to remind everyone that we do have some upcoming webinars, including tomorrow's part 4 for this webinar series. ACI also offers our webinars in on-demand format. That does conclude our presentation for today. We hope you'll choose to join us for future learning opportunities. Have a wonderful afternoon. Thank you.